हेलो स्टूडेंट्स, आज जो क्वेश्चन है उसमें वी आर गोइंग टू प्रूव दैट सीक्वेंस डिफाइंड बाय x1 equals to root 7. First term is defined like this: x1 equals to root 7, and rest of the terms are defined by this recurrence relation xn plus 1 equals to root 7 plus xn. If I want to evaluate the second term, then I will just put n equals to 2 in this term, and x2 will be root 7 plus x1, and that will give root of 7 plus root 7. And similarly, continuing like this, I can find all the terms of the sequence. Now I need to prove that this xn is convergent and converges to the positive root of this equation. So here the sequence is given in the terms of some recurrence relation, right? So let us prove this sequence, whether it is convergent or not. So first of all, we will now we have an intuition that x2 will be root 7 plus some positive value. That means if I take x2 by putting n equals to 1 here, then I will get 7 plus root 7, right? So I have an intuitive idea that this x1 is only root 7 and x2 is root 7 some positive number, right? So from here I can intuitively say that this sequence may be an increasing sequence. So I need to prove that it is an increasing sequence. So let us take now given sequence is x1 equals to root 7 and xn plus 1 equals to root 7 plus xn, right? So we shall prove by our intuition that this is an increasing sequence. We shall prove that xn plus 1 minus xn is greater than 0, or I can write xn plus 1 is greater than xn. Now I will prove this holds for all n belongs to natural numbers. So whenever we talk about natural numbers, so one thing that comes to our mind is principle of mathematical induction. So whenever we prove the results for natural numbers, we can use the principle of mathematical induction. So here we will use principle of mathematical induction right to prove the above result. Now first of all we will take x1. Now x1, we will check whether the result hold for x1 or not. x1 equals to root 7, x2 equals to root 7 plus root of 7 plus root 7, right? So clearly x2 is greater than x1. That is, result is true for n equals to 1, right? Now we will suppose that result is true for some natural number k, and then in third step we will prove that result is true for k plus 1. So let us suppose that the result is true for n equals to some k, right? Where k is a natural number. K is any natural number. Right? So that means that is xk plus 1 is greater than xk. Clearly? So now by using this result, we will prove that result is true for k plus 1. Now how can we prove? Now see, here it is xk plus 1, here it is 7. Now I will add 7 both sides. right? So if I add 7 both sides, because 7 is any real number, so sorry, so inequality remains same, unchanged. So I will take under root both sides. Positive square root of a positive number is again a positive number, so inequality remains unchanged, right? So this is now here I can, this implies this is the xk plus 2 and this is xk plus 1. This is the term k plus 2 and this is term k plus 1. So k plus 2 is greater than k plus 1. That is what it means. The result is true. That is, result is true for n equals to k plus 1. Right? Hence, by principle of mathematical induction, I can write in short form as principle of mathematical induction, PMI. By principle of mathematical induction, the result is true for all n belongs to natural number. That is, xn plus 1 is greater than xn. This holds for all n belongs to natural number. Right? Now what it means? This means that xn is an increasing sequence. So first we have proved that it is an increasing sequence. Now in order to prove that it is convergent, we just need to prove that it is a bounded above sequence. Now we shall prove. Now we shall prove that xn is strictly less than 7 for all n belongs to natural number. Now again, we will use the principle of mathematical induction. Now see how. Again, we will use principle of mathematical induction. Let x1 is under root 7, so clearly it is less than 7, right? So this is obvious, root 7 is less than 7, right? So therefore result is true for n equals to 1. Let us suppose that the result is true for n equals to k. Now what it means? That xk is less than 7, right? So now I need to prove that xk plus 1 is also less than 7. So I will just add 7 both sides. Less than 7 plus 7, and I will take under root. So under root of this 7 plus xk is less than under root 14. Right? Now under root 14 is about the 3 points some value, which is clearly less than 7. Can you see that? Can you observe that root 14 will be clearly less than 7? So, but this is xk plus 1. By our definition of sequence, 7 plus xk is xk plus 1. Root of 7 plus xk is xk plus 1. So this is clearly less than 7. Therefore, that is, we can say, hence, result is true for k plus 1. Hence, here I can write that. Hence, by principle of mathematical induction, result is true for all n belongs to natural number. That is, xn is less than 7 for all n belongs to natural number. Now this implies xn is bounded above. Xn is bounded. Since xn is increasing sequence, monotonically increasing sequence, and bounded above, therefore xn is convergent sequence. So we have proved that xn is convergent sequence, right? So this is the first case we need to prove that we are trying to prove. So this is our first result, that we need to prove that this sequence is convergent. Now secondly, we will prove that this converges to a positive root of the equation. Now as we know, limit, if we take, let limit n tends to infinity, xn equals to y, right? So also limit n tend to infinity, xn plus 1, that will be equal to limit n tend to infinity, because this is a recurrence formula, so I can write the recurrence relation here as xn. So this is again y, and this I can write under root 7 plus y. So this implies y square equals to 7 plus y, or y square minus y minus 7 equals to 0. So from here I can find the value of y, because this is a quadratic equation. Using the formula for the solution of quadratic equation, I will get 1 plus minus under the root 1 plus 28 divided by 2. So this equals to 1 plus minus under root 29 divided by 2. Since these terms are all positive, because xn is greater than 0 for all n, so therefore the sequence will converge to some positive number y only, right? So it will only converge to some positive term y. So y is also greater than 0. So if I neglect the negative term, then I will get, so here, since y is positive, therefore y equals to 1 plus under the root 29 divided by 2. Clearly, xn is converging to y, which is equal to 1 plus under root 29 by 2, and y is the positive root of the equation y square minus y minus 7 equals to 0. So this is the whole solution. So let us revise this solution quickly. So we have given the first term root 7, first term is root 7, and next terms are given by some recurrence relation, xn plus 1 equals to root of 7 plus xn, and we need to prove that this sequence is convergent, and further we need to prove that this sequence converges to the positive root of the equation. So here first we write x1, then we write xn plus 1. In order to prove that this sequence is convergent, we will prove it by using the concept of monotonically increasing or decreasing sequences. So intuitively we get an idea that this sequence is increasing. So we prove this concept, this monotonically increasing concept, by using the principle of mathematical induction. So here there are three steps. First is the result is true for n equals to 1. That is, if I put n equals to 1 here, then I will get x2 is greater than x1. So first I find, we found x1, then we evaluate x2, and clearly x2 is greater than x1, hence result is true for n equals to 1. Let us suppose that result is true for n equals to k, that is xk plus 1 is greater than xk. Now by some simple algebraic operations on this inequality, we will get xk plus 2 is greater than xk plus 1. That means the sequence, this result holds for k plus 1 also. Therefore, by principle of mathematical induction, the result is true for all natural number n. That is, xn plus 1 is greater than xn. Now, see, here we proved that sequence is increasing sequence, monotonically increasing sequence. So, in order to prove that it is convergent, we need to prove that it is bounded above. So, again by some intuition, we can prove that xn is less than 7, right? So, we will prove it by using principle of mathematical induction. So, x1 is equal to under root 7, so which is strictly less than 7. So, result is true for n equals to 1. So, then we suppose that it is true for k, and then again by some mathematical operations on this inequality, just by adding 7 both sides, taking root, and this is again xk plus 1, and it is clearly less than 7 because its value is less than under root 14, and under root 14 is clearly less than 7. So xk plus 1 is less than 7. Hence the result is true for k plus 1. Therefore again by mathematical induction, xn is less than 7 for all natural numbers. So again we have proved that xn is bounded above. So since it is increasing and bounded above, therefore it is convergent. Now we will prove that it is converging to some positive root of this equation. So here we suppose we limit this, that xn is converging to y. So xn plus 1 will also converge to y, and xn plus 1 is 7 plus xn. So we can write 7 plus xn as y. So y plus equals to under root 7 plus y. So by solving this equation, first we get the quadratic equation, and then we get the solution. So where y is the limit of this sequence. Y is the real number into which xn is converging, and its value is 1 plus root 29 by 2, and clearly it is the positive root of this equation, right? So xn is converging to the positive root of this equation, that we all need to prove. So I hope the idea is clear. Now we will move to the next question, very important and a little bit difficult to understand. So I need your full concentration to understand this question, otherwise you will skip some points. So to solve this question, let us see what is the statement. Prove that xn, where xn is 1 plus 1 by n raised to power n. So it is some binomial expression. This is monotonically increasing, bounded, convergent, right? So same concept we are using. And the extra thing is its limits lie between 2 and 3. This is simple because we will prove that it is bounded. So it lies, all the terms lie 2 and 3, and obviously the xn is converging to the limit between 2 and 3. So there is not any new thing in this third part. So we need to concentrate only these two, monotonically increasing and bounded. Bounded means we need to prove that it is bounded above as well as bounded below. So in order to prove this question, we will use these three results, these three simple inequalities. First is 1 minus k upon n plus 1 is greater than 1 minus k upon n. Now this is some simple expression. K is any fixed number, natural number. N plus 1 is again a natural number. So 1 minus k upon n plus 1 is greater than 1 minus k upon n. Now see, uh, this k is fixed and n plus 1 is varying. N is varying. So here it is n plus 1 and here it is n. So denominator is larger, so number is small. So something is subtracting from 1. Here it is a small number and here it is a large number. So whenever we subtract a small number, that number will be greater. So 1 minus k upon n plus 1 will be greater than 1 minus k by n. Again I am repeating this. This number is small, this number is large. Whenever we subtract some number, some smaller number, then that whole term will be greater. I hope the idea is clear what I am trying to convince. Second is, this is very simple. 1, if I subtract some positive number, then obviously that number will be smaller. So 1 minus 1 by n will be less than 1. So here I am just subtracting 0 and here I am subtracting some positive number. So obviously 1 is greater than 1 minus 1 by n. Third result is, this is the important result. 1 upon n factorial is strictly less than 1 upon 2 raised to power n minus 1. So this is the standard result. I will not go to the proof. I will, as it is, use this result. Sorry. So let us start this result. Xn equals to, this given sequence is 1 plus 1 by n raised to power n. This is the binomial expression. So I will open this expression by using binomial theorem. So the result will be 1 plus n into 1 by n plus n into n minus 1 upon 2 factorial 1 by n square. Yeah, I can write here it as 1 by n square plus n into n minus 1 into n minus 2 upon 3 factorial 1 by n cube plus so on, and last term is n into n minus 1 into n minus 2 and so on, n minus n minus 1 whole divided by n minus 1 means a last term will be 1, right? Whole divided by n factorial into 1 by n raised to power n. So this is the last term of the binomial expression, right? So I will rearrange these terms. Please see carefully. 1 plus, this is again 1 plus, now I will 1 by 2 factorial I will take out, and n square minus n divided by n square, that will give 1 minus 1 by n. Yeah. Yes, can you please observe this, what I have done? Plus 1 upon 3 factorial is again outside. So this is n cube plus 2n square plus 2, right? Now this here I can write it as 1 minus 1 by n. If I will, I can simply cut it down, like I combine, first I will cancel 1n, and with second term 1 minus 1 by n, and with third term 1 minus 2 by n. So I can write 1 minus 2 by n, and so on. And last term will be here, one term will be cancelled out, second term is 1 minus 1 by n, third term is 1 minus 2 by n, and so on. Last term is 1 minus n minus 1 by n. and 1 upon n factorial is out. So these are the terms. Please observe this carefully. What I have done, I have just combined this term, this denominator term with the numerator term, this denominator term with the numerator term, this denominator term with the numerator term, and rest factorials are remained as it is. So this is the accent term. If you are clear about, then you can easily see what will be xn plus 1. I will write xn plus 1, and I will just replace n by n plus 1. So here it is 1 plus 1 plus 1 by 2 factorial, 1 minus 1 upon n plus 1 plus 1 upon 3 factorial, 1 minus 1 upon n plus 1 into 1 minus 2 upon n plus 1, and so on. This will be the second last term, and next term will be n plus 1 factorial, last term, 1 minus 1 upon n plus 1, 1 minus 2 upon n plus 1, and so on, and last is 1 minus n upon n plus 1. Right? Now I need to observe this carefully. So I want to check whether n plus 1, xn plus 1 is greater or xn is greater. Right? So please observe this carefully. First term are same, second term is same, third term 1 minus 1 upon n and 1 minus 1 upon n plus 1. Can you see which term is greater out of these two? I am using the first result. 1 minus k upon n plus 1 is greater than 1 minus k by n. So 1 minus 1 by n is greater, or 1 minus 1 upon n plus 1 is greater. Please observe it from here. Here k is 1. For first term k is 1. For second term k is 2. Now clearly out of these two, this term is greater. Again, if you compare these two terms and these two terms, this term is greater. Again, this term is greater. So, and so on. You can compare here also. So obviously, the xn terms, xn plus 1, the terms in xn plus 1 is greater than the terms in xn. And these are n plus 1 terms and these are n terms. So obviously, I can say that the terms in xn plus 1 is greater than xn, so therefore xn plus 1 term will be greater than xn. So here I will write, since each bracketed term in xn plus 1 is greater than the terms in xn. That is, I will write this result. This holds for all n. Therefore, I can say that xn plus 1 is strictly greater than xn. This holds for all n belongs to H denomination. That is, sequence xn is monotonically increasing sequence. Right? So it is monotonically increasing sequence. So this is the first part. Now let us move to the second part, bounded part. Now, again let us write xn. I will copy the xn from here. I'm using the technology.